Almost everything we know about stars depends on our first having an idea of how far away they are. In this assignment, we'll work on two different ways we can use to calculate the distances to stars. We'll also see how we can convert the uncertainty in what we measure into an uncertainty in the distance. In this case, we're trying to find the distances to the stars in your constellation. The constellation file gives enough information to let you calculate distances a couple of different ways. So in this question, we'll practice both of them to see how close they are. In addition, we're going to estimate the uncertainty in one of those distance measurements. This will let us know whether the two measurements are actually in agreement or not. The question itself doesn't give us any values we need for the calculation, so we can leave that box blank. For our prediction, we have just one thing we need to determine: which star is closest to us. There are a couple of ways we can do this as well, but the simplest one is to use the parallax information. Remember that there is a very simple relationship between how large the parallax is and how far away the star is. So you can use this to predict which star is closest. Remember to give the reason for your prediction. We're going to be doing two different types of distance calculations here, so we need two different equations. The first one is the magnitude-distance relationship. D equals 3.26 light-years times 10 to the power of little m minus big M plus 5 divided by 5. The d here is the distance to the star in light-years. Little m is the apparent magnitude, while big M is the absolute magnitude. Note that it's actually not easy to measure the absolute magnitude directly, but we can often get an estimate of it from the star's spectral luminosity type. Remember that the fraction here is all in the exponent. As a result, you need to calculate the value of the fraction first, then find 10 to the power of that using the 10 to the x key in your calculator. The other equation we need is the parallax equation. D equals 3.26 light-years divided by p. Again, d is the distance in light-years, and now p is the parallax angle. So the numbers we need to look up from the constellation file will be the absolute and apparent magnitudes from all three stars you'll be calculating. In addition, you'll need the parallax and the parallax uncertainty for these. Make sure you include the star you predicted would be closest to us. In this question, there is no unit conversion, so we can leave that box blank. Now we can go ahead and calculate the distances from the magnitudes. Let's look at an example of a star that has an apparent magnitude of 4 and an absolute magnitude of -2. Remember that the lower or more negative the number, the brighter the star is. So the apparent magnitude of 4 tells us that the star isn't very bright in our sky. You probably couldn't see it from a light-polluted sky. On the other hand, the absolute magnitude of -2 means that it's a very luminous star. It puts out much more energy than our own sun. Since it's a luminous star that's not very bright in our sky, it's probably pretty far away. So put the values into the equation. We'll work through this in a couple of steps. First, we'll calculate the fraction in the exponent. Remember to be careful with the -2. The fraction is 11 over 5, or 2.2. 10 to the power of 2.2 is 158. Remember to use the 10 to the x key on your calculator for this step. Also, don't forget that 10 to the 2 is 100, so getting a little more than that for 10 to the 2.2 makes sense. Finally, we multiply that by 3.26 light-years to get a distance of 517 light-years. You'll want to repeat this calculation for the three stars in your constellation that you're calculating. The other way of calculating the distance is to use the parallax. Remember that parallax is a measure of how much a star appears to move back and forth in the sky as the Earth orbits the Sun. You only need to do the parallax calculation for the star that turned out to be closest to us in the magnitude calculations. But in addition to finding the best fit distance, you'll also need to find what the range of possible distances is based on how uncertain our measurements are. Let's give an example of a star with a parallax of 0.0061 arcseconds, with a parallax uncertainty of 0.0006 arcseconds. First, we calculate the distance using the parallax measurement. This gives 3.26 light years divided by 0.0061 arcseconds, leaving us with a distance of 534 light years. That's close to the same distance we calculated using magnitudes, but we'd like to know if it's close enough. No measurement is infinitely accurate, and in this case, we also know how uncertain our parallax measurements are. The parallax uncertainty of 0.0006 arcseconds means that the actual parallax could be as small as 0.0055 arcseconds, or it could be as large as 0.0067 arcseconds. So in order to estimate the range of distances this star could be, we should redo the calculation with these upper and lower values for the parallax. When we do the higher parallax, we get a lower distance of just 487 light years. When we use the lower value of the parallax, the distance comes out to 593 light years. So this star could be anywhere from 487 to 593 light years away from us. The distance we measured with magnitudes, 517 light years, is consistent with that answer. Note that there's also an uncertainty in the magnitudes, but we don't have that information in the constellation table. Now it's time to look over the answers and decide if they make sense and agree with your predictions. Did you see the relationship between parallax values and distances calculated that you expected to see? There are a few things that could suggest problems with the calculations. You know that the closest star is just over 4 light years away from us. So if you're getting distances less than that, it means there's something wrong with the answer. For most constellations, the largest distances you're likely to see will be no more than several thousand light years away. Within the plane of our galaxy, it's hard to see individual stars much further away than that. On the other hand, if you have the constellations Tucana or Dorado, you might have one or more stars that are more than 100,000 light years away. That's because these two constellations contain small satellite galaxies of our Milky Way, and with the telescope, we can see individual stars within them. Another sign of a possible problem in the calculations is if the two ways of calculating the distance come up with very different results. The two measurements should usually agree within the uncertainty in values, so if they're far apart, it suggests something may have gone wrong. Remember, if you're having trouble deciding, it's okay to ask for help. Also, don't forget to answer the comparison part even if everything agrees.